Hello, welcome back. In section 1-2, we do a little bit more playing with initial value problems. Also called particular solutions. So our first one, we'll start by being asked to verify y equals ce to the minus x plus x minus 1 is a family of solutions to the differential equation y prime is worth x minus y. After that, we'll find a solution that satisfies a given initial condition. So for this one, they want y of 0 to be worth 10. So they sort of, in differential equations, you'll see that quite a bit, that they sort of borrow function notation and keep it in a y format instead of giving it a name like f of x or g of x. So for the solution of part 1, we were given y is ce to the minus x plus x minus 1. In our differential equation, the highest order derivative we have is a first derivative, so we'll just find y prime. So y prime would be minus ce to the minus x. So it's just derivative of e to the minus x is minus e to the minus x and multiply by the c. And we have plus 1. So then in our diff EQ, left-hand side is the y prime. That is equal to, then by substitution, minus c e to the minus x plus 1. On the right-hand side, we had x minus y, which is x minus, and then we can sub in for what y is the same as. We said y is worth c e to the minus x plus x minus 1. We can go ahead and knock down those parentheses. So x minus ce to the minus x plus 1. And we have the x minus x, those will drop. So our right-hand side is now minus ce to the minus x plus 1. And notice that is equal to the right-hand side. So we have verified that yes, this does work. This does give us a solution. We get an identity. Minus ce to the minus x plus 1 is equal to minus ce to the minus x plus 1. So then the second part is, okay, well, that's a family of solutions. What they mean by a family of solutions, if c were any real number, non-zero real number constant, so say maybe 1,000. 1,000 e to the minus x plus x minus 1 will satisfy the differential equation. If c were negative pi over 19, plugging that into the original will still satisfy the differential equation. So what they're saying here is that when we plug in an x value of 0, we get a y value of 10. That will give us the c value if we plug into the original. So in step 2, finding the particular solution given the initial condition, our y value that they asked us for was a 10. Is equal to, we don't know c yet, that's what we're solving for, e to the opposite of x is 0. They gave us y of 0. plus 0, plus, my apologies there, minus 1. So we can now solve this thing for c. So we have 10 is worth c over 1 is still just c, and we have plus 0 minus 1, so minus 1, so c is 11. So then our particular solution for the given initial condition would be y equals 11 e to the minus x plus x minus 1. So while we have an infinite family of solutions for different values of c, only one of them goes through this point of 0, 10. And we do sometimes work with 2-parameter families of solutions. So on this one, we're going to be given, let's say x is worth c1 sine of 9t plus c2 cosine of 9t and that's going to be a family of solutions to x double prime plus 81x is equal to 0. So they've told us that this works, and we want to find a solution given initial conditions. Excuse me. So here they're going to tell us x of pi over 18 is worth 5, and x prime of pi over 18 is worth 4. So we can see, okay, we need at least a first derivative, if not a second derivative, to get this thing going. If we were confirming it, we would need to do a second derivative as well. But let's start with x prime of t. So also equivalent to saying find dx dt. So we'll hang on to c1, and we'll differentiate sine of 9t with respect to the variable t. So that would be 9 cosine of 9t. Hang on to your c2 and differentiate cosine of 9t with respect to the variable t. So times negative 9 times sine of 9t. And we can do a little cleanup on that. So x prime of t, we're usually writing the known constant out front, so 9c1 cosine of 9t minus 9c2 sine of 9t. And if you want to verify the solution, x double prime, hang on to your 9c1, derivative of cosine of 9t, negative 9 sine of 9t, hang on to minus 9c sub 2, differentiate sine of 9t, so that's times 9 cosine of 9t. So x double prime of t, negative 81 c sub 1 sine of 9t, minus 81 c sub 2 cosine of 9t. And you can kind of see then, I won't write up the whole thing since they didn't ask us to verify. If you take this and add 81 times the original, we will get a 0 as our result. All right, so let's start with these initial conditions then. So they tell us x of pi over 18 is worth 5. So our output is 5. We don't know the value of C1 yet. Then we have sine of 9 times t. The t value they had us plug in was pi over 18. Plus c sub 2 cosine of 9 times pi over 18 again. So a little simplifying there, 5 is worth c sub 1 sine of pi over 2 plus c sub 2 cosine of pi over 2. Cosine of pi over 2, though, is 0. Sine of pi over 2 is 1, so 5 is worth c1 times 1, or just c1 is equal to 5. Let me bring the relevant information to the next page. So we know that x prime of t we figured out on the previous page, and I'll do the cleaned up version, 9c sub 1 cosine of 9t minus 9c sub 2 sine of 9t. And we're also told that we have the initial condition x prime of pi over 18 is worth 4. We do know c sub 1 is worth 5 already. So by substitution, our output should be a 4. 9 times c sub 1 we know to be a 5. Cosine of 9 times, we're plugging in a t value of pi over 18. Minus 9 times c sub 2 sine of 9 times, once again, our input of pi over 18. That is one ugly little pi there, sorry. All right, so a little cleanup work. So 4 is worth 45 cosine of pi over 2 minus 81 c sub 2 sine of pi over 2. My apologies, minus 9 c sub 2 sine of pi over 2. Cosine of 90 degrees, though, is 0. Goodbye to that term. So then 4 is equal to negative 9 c sub 2. Sine of pi over 2 is 1. So times 1, we don't have to write the times 1, so divide both sides by negative 9, and c sub 2 is negative 4/9. So then we want to tell them what the particular solution is. So they told us x is equal to, just as a reminder from the other page, c sub 1 sine of 9t plus c sub 2 cosine of 9t. So our particular solution, given the two initial conditions, x is equal to 5, so c1 we figured out was 5 sine of 9t plus a negative 4/9, so just minus 4/9 cosine of 9t. So that would be our particular solution given the 2-parameter initial condition they gave us of what the first power looks like and what the first derivative looks like. All right, so the next thing we take a look at is a theorem. Let's just start a fresh page for our theorem here. Theorem 1.2.1 on the existence of a unique solution. If you end up going a little bit further in math and get to some of the courses involving proofs and a little bit more writing, there's a little common math shorthand for some of that. Backwards capital E for there exists. If there is an exclamation mark after it, there exists a unique ... whatever follows. So just a little preview to help you if you're reading ahead in any of your other math courses. So this verifies that there exists a unique solution when we meet the conditions in this theorem. So if f of xy and partial of f with respect to y are continuous on region R, and there exists interval I naught I sub 0 x naught minus h, x naught plus h. H is just some arbitrarily small positive constant. And we're on close interval AB. Unique function y of x on I naught. It is a unique solution to the initial value problem. In English, what this is saying is we have a unique solution where the derivatives are defined. So, for example, determine region where there exists a unique solution. Y squared minus 25 quantity times y prime is worth x minus 4. So first thing I'll do is get this y prime by itself. A little bit of factoring, and y prime is difference of x and 4 over product of the sum and the difference of y and 5. So some places where the derivative is defined, basically anywhere but 5 or negative 5. So our interval where we have unique solutions, we can use y on negative infinity, negative 5, or we could do negative 5 to 5, or we could say we have a solution on 5 infinity, but we can't claim we have unique solutions everywhere. The derivative is undefined at -5 and +5. So when you're stating your interval, basically say, okay, well, what is it that I have to do to avoid the derivative being undefined? So in section 1-2, I would recommend 1 to 27, the odds, 31 and 35 to 43, also on the odds. So if you have questions, please get in touch with me. Otherwise, I will see you next time. Stay safe out there.